Hello there, and welcome to Sleepy Science Vault. For thousands of years, every culture that looked up at the night sky carried roughly the same quiet assumption. Whatever the universe was doing, it had to be settling down, slowing, calming, easing towards some final stillness. Gravity pulls. It always has. Throw a ball into the air, and eventually it falls back down. So if the universe began with a tremendous outward burst, the way the Big Bang Theory describes, it seemed only logical that gravity would gradually be pulling on the reins of that expansion ever since, easing the cosmos toward a slower and slower pace. For most of the 20th century, that's exactly what scientists expected to find once they had the tools to check. They were wrong. In the late 1990s, two separate teams of astronomers, working independently, without any contact with one another, set out to measure exactly how much the expansion of the universe was decelerating. They were confident in the question. They simply wanted to know the number. And what they found, when the data finally came together, was something that no one in either team had been prepared for. The universe wasn't slowing down at all. It was speeding up. At first, many of the researchers involved assumed they'd made some kind of error. A flaw in the instruments, perhaps, or a miscalculation buried somewhere in the math. Results this strange tend to get checked, and rechecked, and checked again, before anyone is willing to believe them. But the numbers held. Every recalibration, every new batch of data, kept pointing toward the same impossible conclusion. To understand how they reached it, it helps to know what they were actually studying. The astronomers were observing a very specific kind of stellar explosion, known as a type Ia supernova. These occur when a dense, collapsed star called a white dwarf pulls in just enough material from a nearby companion to cross a precise mass threshold, and when it does, it detonates in almost exactly the same way, every single time, regardless of where in the universe it happens. That consistency makes these explosions remarkably useful. Astronomers often call them standard candles, because their true brightness is so predictable that by measuring how dim they appear from Earth, scientists can calculate, with real precision, just how far away they actually are. So the teams plotted dozens of these ancient explosions, scattered across billions of light years, and compared their distances to how quickly the galaxies around them were racing away. If the expansion of the universe had been slowing, as gravity demanded, the more distant supernovae should have appeared brighter than expected, closer than their age implied. Instead, they appeared dimmer. Farther away than they should have been, as if space itself had been stretching faster and faster the longer it had been allowed to expand. There was only one explanation that fit the data. The expansion of the universe was accelerating, and had been for billions of years. This discovery didn't rest quietly within just one experiment. In the decades since, it has been tested again and again, through entirely different methods. Observations of the cosmic microwave background, the faint, ancient light still drifting through space from not long after the Big Bang itself, lined up with what the supernovae had revealed. Massive surveys mapping how galaxies cluster together across the universe told the same story. Each method approached the question from a different direction, using different instruments, different teams, different decades of technology. And each one arrived, independently, at the same unsettling answer. Scientists gave this mysterious push a name. They called it dark energy. There's a strange echo buried in this story, one that reaches all the way back to Albert Einstein. Long before any of this was discovered, Einstein had added a term to his equations of general relativity called the cosmological constant, a kind of built-in counterforce meant to keep the universe perfectly still, neither expanding nor collapsing. When Edwin Hubble later showed that the universe was expanding, Einstein is said to have considered the idea one of the greatest blunders of his career, and quietly set it aside. Decades later, almost as if the universe were returning the favor, that same abandoned idea resurfaced as one of the leading candidates for explaining the very acceleration Einstein never saw coming. And yet, naming dark energy was never the same as understanding it. This is where the story turns genuinely strange, because even now, with satellites circling the planet and decades of careful research behind us, nobody actually knows what dark energy is. We can measure its effects with extraordinary precision. We can see how it stretches the fabric of space, pushing galaxies apart faster than gravity could ever hope to pull them back together. But ask what it's actually made of, where it comes from, why it exists at all, and the answers dissolve into open questions that no one has been able to close. Is it simply a property of empty space itself, a steady hum built permanently into the vacuum, present everywhere at once? Or is it something more dynamic, a field whose strength shifts subtly across the long history of the cosmos? Physicists have proposed many models over the years. None of them has been confirmed. Dark energy remains one of the deepest unsolved mysteries in modern science, a force whose fingerprints stretch across the entire observable universe, while its true identity stays just out of reach, like a shape glimpsed only in shadow. What makes this mystery even harder to sit with is the sheer scale of it. Dark energy isn't some minor adjustment, some small correction tucked into the margins of cosmology. It is, by far, the single largest component of the universe. According to the most precise measurements astronomers have ever gathered, drawn from spacecraft that map the cosmic microwave background in extraordinary detail, dark energy makes up roughly 68% of everything that exists. Let that settle for a moment. More than 2/3 of the entire universe is something invisible, something untouchable, something we still cannot fully explain. Everything familiar to us, the stars scattered across the night sky, the planets quietly orbiting them, every grain of dust, every person who has ever lived, amounts to only a small fraction of the total. Even dark matter, that other deep mystery threaded through the cosmos, makes up far less than dark energy does. Ordinary matter, the stuff of galaxies and human bodies alike, is almost an afterthought beside it. These numbers haven't come from a single study, run once and accepted on faith. They've been measured again and again, by different spacecraft, different surveys, different generations of scientists working more than 2 decades apart, and they keep arriving at the same conclusion. The universe we live in is overwhelmingly shaped by something we cannot see. So as your mind drifts through the quiet, growing darkness between galaxies, as you imagine that vast emptiness stretching wider with every passing moment, remember that the darkness isn't truly empty at all. It is humming, invisibly, with something more powerful than gravity itself, gently easing the universe apart, fact by fact, galaxy by galaxy, into a future we are only just beginning to understand. If you could travel to the farthest edge of what telescopes have ever managed to see, out past galaxies so distant that their light left home before the Earth even existed, you would find something curious waiting for you there. The same invisible presence that surrounds us here, in this quiet corner of the universe, is also out there, just as strong, just as steady. Dark energy doesn't gather in clumps. It doesn't pool around galaxies or trail behind clusters of stars the way matter does. As far as scientists can tell, it appears uniformly everywhere, spread with remarkable evenness across the entire fabric of space, from one end of the observable universe to the other. That evenness is part of what makes it so hard to study. Most things in physics reveal themselves through contrast. A star glows brighter than the space around it. A planet blocks light as it passes in front of its sun. Even dark matter, mysterious as it is, gathers densely enough in certain regions to bend light as it passes by, leaving a kind of fingerprint scientists can trace. Dark energy offers nothing like that. There is no brighter patch to point a telescope toward. No shadow. No clump to map. It cannot be directly detected, not by any instrument built so far, and perhaps not by any instrument that could ever be built using methods like these. So how do we know it's there at all? The honest answer is that we don't see dark energy. We see its consequences, and from those consequences, we infer that something must be causing them. Scientists only know dark energy exists because of how galaxies are moving, how supernovae appear dimmer than expected, how the geometry of space itself seems to be stretching in ways that nothing else can explain. It's a bit like standing in a sealed room and feeling a steady wind on your skin, without ever being able to see what's producing it. You can't point to the source. But the evidence brushing past you is undeniable. This is also where a common confusion tends to creep in, one worth clearing up gently. Dark energy is often mentioned in the same breath as dark matter, and it's easy to assume they're simply two names for the same mystery. They are not. Dark matter is something that clumps, something that adds extra gravity to galaxies, holding them together more tightly than their visible matter alone could explain. It behaves, in many ways, like ordinary matter that simply doesn't emit light. Dark energy is something else entirely. It doesn't pull things together. It pushes them apart. The two phenomena share a kind of poetic darkness in their names, an acknowledgement that both remain hidden from direct observation, but their behavior, their role in the cosmos, their very nature, are almost opposites of one another. And in some ways, dark energy may be the deeper mystery of the two. Dark matter, mysterious as it is, still behaves the way gravity has always behaved. It attracts. It clusters. It follows patterns that fit comfortably within physics as we already understand it, even if we can't yet say exactly what particle it's made of. Dark energy doesn't offer that comfort. It doesn't fit neatly into the gravitational story at all. It seems to require something new, some property of the universe that physics hadn't anticipated, and still struggles to explain. Many researchers consider it the more unsettling of the two unknowns, precisely because it challenges something more fundamental than what particles exist. It challenges how space itself behaves. To understand why that's so strange, it helps to think about what dark energy actually does. Every galaxy in the universe is, in some sense, falling away from every other galaxy. Not through any motion of its own, the way a rocket moves through space, but because the space between galaxies is itself expanding, stretching, slowly and steadily, carrying galaxies apart the way raisins in a rising loaf of bread drift farther from one another as the dough expands around them. Dark energy is the force believed to be driving that stretching forward, gently and relentlessly pushing galaxies apart from one another, faster with each passing era of cosmic time. This is where dark energy reveals just how strange a character it truly is, because everywhere else in nature, gravity pulls. It draws planets into orbit. It holds galaxies together. It pulls falling objects toward the ground. Dark energy works against that pull. It behaves like something almost impossible within the old framework of physics, a kind of repulsive gravity, a force that pushes outward instead of drawing inward. Imagine if gravity, instead of bringing two objects together, gently nudged them apart instead. That's something close to how dark energy seems to behave on a cosmic scale. This single trait is what makes dark energy responsible for the very discovery that revealed it in the first place. Ordinary matter, all on its own, should be slowing the expansion of the universe down. Gravity from all that mass, stars, galaxies, gas, dust, should be acting like a brake, gradually pulling everything back toward a slower and slower rate of expansion, the way Earth's gravity quietly pulls a thrown ball back down no matter how hard it was thrown. And yet that braking effect isn't what we observe. Matter should be slowing the expansion of the universe. Instead, the expansion keeps accelerating, as though something is pressing down on the gas pedal even as gravity tries to apply the brakes. Dark energy appears to be exactly that, a force strong enough to overpower the combined gravitational pull of everything else in existence. What makes this even more remarkable is that dark energy doesn't behave like ordinary matter at all, not even invisible matter. It doesn't dilute the way matter does as the universe expands. If you stretch out a fixed amount of gas across a larger volume, its density drops, because the same amount of material is spread more thinly. Dark energy doesn't seem to thin out that way. As space grows larger, dark energy doesn't become weaker. If anything, its overall influence grows stronger, because there is simply more space for it to act within. This has led many physicists to a particularly striking idea, that dark energy may not be a substance scattered through space at all, but something built directly into the structure of space-time itself. Not a thing floating within the universe, but a property of the universe, an intrinsic feature of empty space, present in every cubic inch of the cosmos, however far that space may stretch. It's a strange thought to sit with. That the emptiness between galaxies isn't simply nothing. That space itself may carry an energy of its own, quietly written into its very fabric, expanding and pushing outward as a fundamental part of what space is, rather than something extra placed within it. Scientists are still searching for ways to test that idea more precisely, watching distant galaxies with greater care, measuring the universe's expansion across different chapters of cosmic history, hoping to learn whether this mysterious push has remained perfectly constant since the beginning, or whether it has shifted, ever so slightly, as the universe itself has aged. For now, what remains certain is simply this. Something vast, something silent, something woven into the very geometry of space, is steadily carrying the universe outward, galaxy by galaxy, era by era, toward a future shaped by a force we can measure, but still cannot fully name. Once dark energy was confirmed as something real, something woven into the structure of the cosmos itself, scientists were left facing an even larger realization. This wasn't a minor adjustment to existing theories. Dark energy had become, by far, the dominant influence shaping how the universe evolves from this point forward. It isn't simply present alongside matter and radiation, taking a quiet seat among other ingredients. It has become the main author of the universe's unfolding story, the force most responsible for deciding where everything is headed next. To understand how astronomers arrived at such a sweeping conclusion, it helps to go back to the moment before anyone suspected dark energy existed at all, back to a routine measurement that quietly turned into one of the great detective stories in the history of science. The story begins in the 1990s, with two separate research teams, the High-Z Supernova Search Team and the Supernova Cosmology Project, both turning the Hubble Space Telescope toward a very particular kind of light. They were hunting for Type Ia supernovae, those reliable stellar explosions whose true brightness can be calculated with remarkable precision, making them useful as cosmic measuring sticks. Their goal seemed almost mundane at the time. They simply wanted to measure how quickly the expansion of the universe was slowing down, since nearly every model of cosmology assumed gravity must be gradually putting the brakes on everything. What Hubble's observations revealed instead caught both teams completely off guard. The distant supernovae weren't behaving the way a decelerating universe should make them behave. They appeared too dim. Fainter than expected, given how close they seemed to be based on the stretching of their light, what astronomers call redshift. And in this kind of measurement, fainter almost always means farther away. These ancient explosions were sitting at greater distances than a slowing universe could possibly explain. The only way to account for it was if the space between Earth and those supernovae had been stretching faster than anyone had built into their calculations. It was the sort of result that demands to be questioned before it's believed. So it was checked, recalibrated, and checked again, by skeptical scientists fully expecting to find their own mistake. The mistake never appeared. As the picture came into focus, researchers realized they weren't looking at a single strange anomaly. The conclusion rested on three separate, independent lines of evidence, each one arriving at the cosmos from a completely different angle. The supernova observations formed the first pillar. The second came from extraordinarily detailed maps of the cosmic microwave background, the faint afterglow still drifting through space from the universe's earliest moments, which revealed subtle patterns that could only be explained if some unseen ingredient, beyond ordinary matter and beyond dark matter, made up the majority of everything that exists. The third pillar emerged from studying how galaxies cluster together across enormous distances, tracing a kind of ancient rhythm frozen into the large-scale structure of the universe, a rhythm that lined up precisely with what an accelerating expansion would predict. On its own, any one of these findings might have been dismissed as a fluke, an instrument error, a fluke of statistics. Together, they form something far harder to dismiss. Three completely different methods, built on three completely different sets of physics, kept arriving at the very same answer. In the years since, additional methods have only reinforced that conclusion further. Gravitational lensing, the way massive clusters of galaxies bend and distort the light of more distant objects behind them, has offered its own quiet confirmation. Careful counts of how galaxy clusters form and grow across cosmic history have told a remarkably similar story. Each new technique astronomers have devised, often using instruments and approaches the original researchers in the 1990s never could have imagined, keeps strengthening the same unsettling discovery rather than weakening it. There is one piece of evidence, though, that carries a particular kind of elegance, because it comes not from explosions or galaxies, but from the very shape of the universe itself. For decades, cosmologists have wondered whether the universe curves back on itself, the way the surface of a sphere does, or stretches outward in flat, unbending lines, more like an endless sheet of paper. Extraordinarily precise measurements of the cosmic microwave background, gathered by spacecraft mapping the entire sky in painstaking detail, revealed something remarkable. The universe appears to be flat, or so close to flat that any curvature, if it exists at all, is too subtle to detect. That single fact carries enormous weight. A flat universe requires an extremely specific total amount of energy and matter, balanced with exquisite precision, what cosmologists call the critical density. When scientists added together everything they could account for, the stars, the planets, the vast clouds of gas drifting between galaxies, along with dark matter, that other invisible scaffolding holding galaxies together, the total fell dramatically short. Something else had to be filling that gap, something spread smoothly and evenly across the entire universe, making up roughly 2/3 of everything that exists, exactly the amount needed to keep the geometry of space flat. Cosmic flatness, in other words, required dark energy to be real, as though the very shape of the universe had been quietly confirming what the supernovae had already hinted at. By 1998, with the evidence piling up from every direction, this mysterious component needed a name. It was the cosmologist Michael Turner who first used the term that has stuck ever since, dark energy, borrowing the language of its older and equally mysterious cousin, dark matter, while marking it as something fundamentally different underneath the surface. The discovery was significant enough to be honored, in 2011, with the Nobel Prize in Physics, awarded to Saul Perlmutter, Brian Schmidt, and Adam Rees for uncovering the accelerating expansion of the universe. It remains one of the most consequential findings in the history of cosmology, a complete reversal of an assumption that had gone unquestioned for almost an entire century. With the discovery confirmed, and confirmed again through method after independent method, scientists were left facing a quieter, more patient question. If dark energy has always been a part of the universe, why did it take so long for anyone to notice its effects? The answer lies in the long, unhurried history of the cosmos itself. In the earliest chapters of the universe's story, not long after the Big Bang, everything was packed far more densely than it is today. matter, both the ordinary kind and the dark kind, was crowded tightly together, and at that density, gravity held the clear advantage. It pulled inward with tremendous strength, acting like a brake against the universe's outward momentum. For billions of years, gravity dominated the unfolding story of the cosmos, slowing the rate of expansion exactly the way scientists had always assumed it would. But the universe never stopped expanding, even while gravity was winning that early contest. And as space stretched outward, the density of matter began to thin. Spread the same amount of material across a larger and larger volume, and naturally, it grows less concentrated. Galaxies drifted farther apart from one another, and the gravitational pull between them grew correspondingly weaker. Dark energy doesn't behave that way at all. As far as scientists can tell, its density remains essentially unchanged no matter how much space expands around it. It doesn't dilute. It doesn't thin out the way matter does. So as billions of years passed, and matter's gravitational grip continued to weaken, dark energy's steady, unwavering push began to matter more and more in the overall balance of the universe. At some point, somewhere around 5 to 6 billion years ago, the two forces crossed paths. Gravity, weakened by matter spreading ever thinner across an ever larger universe, was finally overtaken by dark energy's quiet, persistent push outward. That moment marked a genuine turning point in cosmic history. The expansion of the universe stopped decelerating and began to accelerate instead, ushering in the very era we find ourselves living in now, the same era that left those astronomers staring, puzzled, at supernovae that simply refused to behave the way the old models said they should. And what comes next, in this very long story still being written, depends on a single question no one has been able to answer yet. Does dark energy remain perfectly constant across the eons, or does it shift and evolve as the universe continues to age? If it turns out to be a true constant, woven permanently into the fabric of space-time itself, then the implications stretch on almost beyond imagining. The acceleration already discovered wouldn't be some passing phase, destined to fade quietly away. It would simply continue. Galaxies visible to us tonight would, over unthinkable stretches of time, drift beyond any horizon we could ever hope to observe again, their light forever out of reach. The distances between things would keep widening, slowly emptying the visible sky of nearly everything except for the structures held tightly enough by their own gravity to resist dark energy's gentle, ceaseless pull, and even those, given enough trillions of years, would eventually grow quiet, and cold, and still. It's a strange thing to carry with you as your own thoughts begin to drift and slow for the night, knowing that somewhere above you, right now, this same process is unfolding. Not urgently. Not violently. Just steadily, the way it has been unfolding for billions of years already, carrying the universe forward into a future shaped by a force we can measure, but still cannot fully name. If you were asked to imagine the emptiest possible place in the universe, a stretch of space far from any star, any galaxy, any wandering speck of dust, you might picture something close to nothing at all. A void. A silence with nothing left to disturb it. But modern physics tells a very different story about emptiness, and it's a story that may finally explain what dark energy actually is. According to quantum theory, even a perfect vacuum, completely stripped of matter, radiation, and anything resembling a thing, is never quite as still as it appears. At the smallest scales imaginable, far smaller than atoms, far smaller than anything a microscope could ever resolve, empty space seems to bubble with a kind of restless activity. Particles and their antiparticles flicker briefly into existence, then vanish again almost instantly, borrowing energy from nothing and paying it back before anyone could ever hope to catch them in the act. Physicists call these fleeting appearances virtual particles, and while no single one of them lasts long enough to be observed directly, their combined, cumulative presence suggests something profound. Empty space may not truly be empty. It may carry an energy of its own, built into the very vacuum itself. This idea has a name. Scientists call it vacuum energy, and it offers one of the most elegant explanations yet proposed for dark energy. If space itself carries a small, constant energy density, spread perfectly evenly no matter where you go in the universe, then that energy would behave in exactly the way astronomers have observed dark energy behaving. It wouldn't dilute as space expands, because more space would simply mean more vacuum, and therefore more of this built-in energy. It would push outward, uniformly, gently, everywhere at once. In other words, vacuum energy looks, on paper, almost exactly like dark energy ought to look. And here's where the story circles back, quietly, to a chapter that began decades before dark energy was ever discovered. This vacuum energy may be precisely what Einstein was imagining when he first introduced his cosmological constant, that mathematical term he added to his equations of general relativity, intended to hold a static universe in perfect balance. He abandoned the idea once Hubble showed the universe was expanding, considering it an unnecessary complication, perhaps even an embarrassment. But the mathematics of the cosmological constant and the physics of vacuum energy turn out to resemble one another so closely that many physicists now treat them as two names for the very same underlying reality. An idea Einstein once discarded may have been sitting quietly inside his own equations all along, waiting nearly a century to be recognized for what it actually was. It's a remarkable possibility. But it leads to a question with real weight behind it, one that cuts to the foundations of physics itself. Either dark energy is genuinely real, a true substance, or a true property of space, existing independently of anything else we understand, or something is fundamentally wrong with our theory of gravity. There isn't really a comfortable middle ground here. The universe is accelerating. That much has been confirmed again and again, through independent methods, by independent teams, across more than 2 decades of careful observation. So either there is some unseen energy out there, doing exactly what dark energy appears to do, or general relativity itself, the theory that has correctly predicted nearly everything else about gravity for over a century, breaks down at the very largest scales the universe has to offer. It's a genuinely uncomfortable choice, and physicists have spent years trying to find a way out of it. As it happens, the first option, the idea that vacuum energy is dark energy, leads almost immediately into one of the strangest, most humbling problems in the entire history of science. Because when physicists actually sat down and tried to calculate how much energy quantum theory predicts should be hiding in empty space, using the best understanding available of particle physics and quantum fields, the number that came out was almost beyond comprehension. It wasn't simply larger than what astronomers had measured dark energy to be. It was larger by a factor that defies ordinary description, somewhere in the range of 10 to the 120th power times 2 large. A number so vast that comparing it to anything familiar barely helps. It would be like predicting the weight of a single snowflake, and instead calculating something heavier than every star in every galaxy in the observable universe, combined, many times over. This staggering gap has come to be known, only half-jokingly, as the worst prediction in the history of physics. And it isn't a minor inconvenience tucked away in some obscure corner of theory. It cuts straight to the heart of how quantum mechanics and gravity are supposed to fit together, two of the most successful frameworks ever developed, both confirmed by extraordinary precision in their own domains, and yet seemingly unable to agree on something as basic as how much energy ought to exist in nothingness itself. Nobody has solved this discrepancy. Some physicists suspect there must be some deep cancellation at work, some hidden symmetry of nature that quietly subtracts almost all of that enormous predicted energy, leaving behind only the faint, residual trace that astronomers actually observe pushing the universe apart. Others wonder whether the entire approach is missing something more fundamental, whether quantum field theory, brilliant as it is at describing particles and forces, simply isn't built to handle a question this large, one that reaches all the way down into the structure of space and time itself. This uncertainty is part of why a second path has remained genuinely open all this time, running alongside the search for vacuum energy rather than replacing it. What if dark energy isn't a substance or an energy at all? What if, instead, our understanding of gravity itself needs to change at cosmic scales? A number of researchers have spent years exploring exactly this possibility, developing what are broadly called modified gravity theories. These frameworks suggest that general relativity, despite its tremendous success in describing how gravity behaves near stars, planets, and galaxies, might quietly diverge from reality once distances stretch out to the size of the observable universe itself. In these models, there is no dark energy in the traditional sense. There's simply gravity, behaving in ways slightly different from what Einstein's equations predict, once you zoom out far enough. So far, none of these alternative theories has managed to outperform the simpler picture, the idea of a cosmological constant or vacuum energy quietly filling space. But they remain seriously studied, tested against new data as it arrives, refined and challenged in equal measure, because the stakes involved are simply too significant to leave any reasonable possibility unexplored. And this, in many ways, is exactly why dark energy has become such a profound puzzle within physics as a whole, reaching far beyond cosmology alone. Whichever explanation eventually turns out to be correct, the implications point towards something genuinely new. If vacuum energy is the answer, then physicists will need to understand why their predictions are off by such an almost incomprehensible margin, a question that may require entirely new physics beyond anything currently known. If modified gravity is the answer instead, then general relativity itself, one of the most thoroughly tested and trusted theories ever devised, will need to be revised at the deepest level. Either path leads somewhere unfamiliar. dark energy may end up being the thread that, once finally understood, unravels into a much larger revolution in how we understand reality itself. Given how much rests on the answer, it should come as no surprise that scientists have spent years devising increasingly clever ways to study dark energy more directly, even without being able to see it, touch it, or capture it in any laboratory. One of the most elegant approaches involves watching how galaxy clusters grow over time. These clusters, vast gravitationally bound cities of galaxies, didn't simply appear all at once. They built up slowly, over billions of years, as gravity drew matter together into larger and larger structures, clumping gas and galaxies into the colossal formations astronomers observe scattered across the universe today. Dark energy, with its steady outward push, works directly against that process. The stronger dark energy's influence becomes, the more it resists gravity's attempt to pull matter into these growing structures, gently suppressing how quickly clusters can form and grow. By carefully measuring how the population of galaxy clusters has changed across different chapters of cosmic history, comparing the universe as it appeared billions of years ago to how it appears today, scientists can effectively measure dark energy's fingerprints written into the large-scale architecture of the cosmos itself. If dark energy has remained constant since the beginning, cluster growth should follow one particular pattern. If it has shifted in strength over time, the pattern should look subtly different. It's a remarkably indirect way of studying something invisible, but in cosmology, indirect evidence, gathered carefully enough, from enough independent angles, can be every bit as convincing as a direct glimpse. One of the most important tools for this kind of work has been the Chandra X-ray Observatory, a space telescope launched specifically to study some of the hottest, most energetic structures in the universe. Galaxy clusters happen to be filled with enormous clouds of superheated gas, glowing brightly in X-ray light, even though that light remains completely invisible to human eyes or ordinary telescopes. By observing this X-ray glow with extraordinary sensitivity, Chandra has allowed astronomers to map the mass, the growth, and the evolution of galaxy clusters across enormous stretches of cosmic time, providing some of the clearest observational evidence yet that dark energy is steadily, measurably, shaping how structure forms across the universe. These observations, combined with supernova surveys, measurements of the cosmic microwave background, and studies of how galaxies cluster together, have allowed scientists to move beyond simply confirming that dark energy exists. They've allowed researchers to begin asking a more refined, more delicate question. Exactly how does dark energy behave? To answer that question with any precision, physicists rely on a single, deceptively simple number, which they call W. This value describes something known as dark energy's equation of state, essentially, the relationship between its pressure and its density, the ratio that determines exactly how it behaves as the universe expands around it. If dark energy is a true cosmological constant, the kind Einstein once imagined, unchanging across cosmic history, then W should equal exactly -1. Every observation gathered so far, every supernova catalogued, every cluster mapped, every careful measurement of the cosmic microwave background, has consistently pointed toward a value remarkably close to that number. Close, but not yet confirmed with absolute, unquestionable certainty. there remains just enough room in the data, just enough uncertainty at the edges of measurement, for the question to stay open. If future observations were ever to reveal that W differs even slightly from -1, the implications would be enormous. It would mean dark energy isn't simply a fixed, eternal property of empty space, but something more dynamic, a field capable of changing in strength as the universe ages, sometimes referred to by physicists as quintessence. Such a finding could reshape not only our understanding of dark energy itself, but the entire future trajectory of the universe, opening possibilities that the simplest models, the ones assuming a perfectly constant force, simply cannot account for. So the search continues, patiently, methodically, one galaxy cluster at a time, one supernova at a time, one increasingly precise measurement of W at a time, as scientists work to coax a little more truth from a universe that remains remarkably reluctant to reveal it. What's striking, when you step back from all of it, is how much has already been learned about something that still cannot be seen, touched, or held. We know how much of the universe it occupies. We know how it has shaped cosmic history, and how it will likely shape what comes next. We've built an entire constellation of evidence around something that, despite every tool modern science has thrown at it, remains every bit as mysterious now as it was on the night someone first noticed those supernovae appearing just a little too dim. And perhaps that's the quiet, strange comfort hidden somewhere in all of this. That even now, surrounded by everything we've measured and confirmed and carefully cross-checked, the universe still holds something back, some deeper layer of itself not yet ready to be fully understood. Somewhere above you tonight, drifting silently between galaxies, that same invisible force is still at work, patiently, steadily, urging everything a little farther apart, waiting, perhaps, for the next careful measurement to bring us one step closer to finally knowing its name. Every story about the universe's distant past eventually arrives at a harder question. Not where did all of this come from, but where is it actually going? For most of the 20th century, cosmologists imagined only two real possibilities for how the universe might end. Either it would expand forever, growing colder and emptier with each passing age, or gravity would eventually win out, pulling everything back together into some final, fiery collapse. Dark energy changed that picture entirely, and in doing so, it opened the door to far stranger possibilities than anyone had previously considered. One of the most unsettling of these is something physicists have come to call the Big Rip. The idea hinges on a simple but chilling possibility, that dark energy isn't just constant, but actually growing stronger as the universe ages. If that's true, then the outward push driving galaxies apart wouldn't simply continue at a steady pace. It would keep accelerating, faster and faster, until it eventually overwhelmed every other force holding the universe together. In the final moments of such a scenario, dark energy wouldn't just separate galaxies from one another. It would tear apart galaxy clusters, then individual galaxies, then solar systems. Planets would be ripped from their stars. The bonds holding stars themselves together would eventually give way. And in the very last fraction of a second, the same relentless stretching would reach down into atoms themselves, pulling apart the particles that make up everything that has ever existed. Not a slow fade into cold stillness, but a finite, definite ending, a complete unraveling of the universe's very fabric. It's a genuinely dramatic scenario, and current observations don't suggest we're heading toward it. But it remains a real possibility within certain models, one that depends entirely on how dark energy actually behaves as billions more years unfold. There's an equally dramatic possibility on the opposite end of the spectrum, one that imagines dark energy doing the reverse of what it appears to be doing now. If dark energy were to weaken over time, rather than strengthen, or if its influence reversed entirely, gravity could eventually reclaim the advantage it lost billions of years ago. In that scenario, the expansion of the universe would slow, then stop, then reverse altogether, with every galaxy beginning to fall back toward every other galaxy. Physicists call this hypothetical ending the Big Crunch, a kind of cosmic homecoming, the universe folding back in on itself, growing hotter and denser as it collapses, mirroring in reverse the very explosion that brought it into being in the first place. What's striking about both of these possibilities, the rip and the crunch, is how much they reveal about just how little we still know. They aren't competing theories so much as bookends, marking out the extreme edges of what dark energy could be doing, depending on subtle details we haven't yet been able to measure with enough precision. Somewhere between those two extremes sits the quieter, more commonly assumed outcome, a universe where dark energy simply remains constant, continuing to push everything apart at a steady, unchanging rate, drifting eventually toward a cold, slow, increasingly empty future, sometimes called the Big Freeze. Which of these futures actually awaits the universe depends entirely on one unresolved question. Is dark energy truly fixed, locked into a single unchanging value for the rest of time? Or does it shift, however subtly, as the cosmos continues to age? For most of the last 2 decades, every measurement gathered pointed towards something very close to constant, close enough that most cosmologists settled comfortably into the Big Freeze as the most likely outcome, with the rip and the crunch treated as interesting but unlikely extremes. Then, in the spring of 2025, that comfortable assumption began to wobble. The story centers on an instrument called DESI, the Dark Energy Spectroscopic Instrument, an international collaboration involving more than 900 researchers spread across over 70 institutions around the world. On March 19 of 2025, the DESI collaboration released a new analysis, and the response it generated reached far beyond the usual circles of academic cosmology. Within weeks, more than 1,500 articles had appeared across the globe, written in dozens of languages, carrying the story to audiences who had likely never heard the words dark energy before. The announcement itself coincided with a presentation at the American Physical Society's Global Physics Summit in Anaheim, California, a moment when one of the deepest assumptions in modern cosmology was quietly, carefully, called into question, in front of a room full of the very physicists who had spent careers building their work on top of it. What DESI reported was this. When researchers combined their own observations with independent data gathered from the cosmic microwave background, from distant supernovae, and from the subtle bending of light known as weak gravitational lensing, the evidence no longer fit comfortably with the simplest model of dark energy, the one where it behaves as a perfectly fixed, unchanging cosmological constant. Instead, something in the data suggested dark energy's influence might be shifting, ever so slightly, across the long arc of cosmic history. Not dramatically. Not in a way that rewrites everything overnight. But enough to suggest that the universe's standard model, the framework cosmologists have relied on for more than 2 decades, might need to be revisited. This wasn't entirely without warning. A full year earlier, in April of 2024, DESI had released its very first results, drawn from just 13 months of observations, and even then, faint hints of this same pattern had quietly appeared in the data. At the time, those hints were treated cautiously, interesting but far from conclusive, the kind of subtle signal that often fades away once more data arrives. Many researchers expected exactly that. Instead, as DESI continued gathering observations, the signal didn't fade. It grew stronger. By 2025, the collaboration had collected and analyzed 3 full years of observations, spanning an almost unimaginable scale, nearly 15 million galaxies and quasars, each one carefully measured, each one adding another data point to what has become the largest 3-dimensional map of the universe ever constructed. Earlier surveys had mapped slices of the cosmos, useful but limited in scope. DESI's map reaches back across roughly 11 billion years of cosmic history, allowing scientists, for the first time, to trace dark energy's influence not just as a single snapshot, but as an evolving story unfolding across most of the universe's entire lifetime. The instrument responsible for gathering all of this sits atop a quiet mountain in southern Arizona, at Kitt Peak National Observatory, mounted on a telescope that has been patiently surveying the sky for decades. What makes DESI itself remarkable isn't simply its location, but its extraordinary mechanical precision. The instrument carries 5,000 individual robotic positioners, each one capable of aiming a hair-thin optical fiber at a single galaxy with an accuracy measured in fractions of the width of a human hair. Each of those fibers captures light from one distant galaxy at a time, allowing the telescope to measure thousands of galaxies simultaneously, night after night, slowly assembling a map of the universe with a level of detail no previous survey had ever achieved. It's worth pausing on that image for a moment. A telescope, sitting quietly under a desert sky, patiently adjusting thousands of tiny mechanical fingers, each one reaching toward a single point of ancient light, gathered from a galaxy that may have stopped existing in its current form billions of years before human eyes ever opened to see it. And from all of that painstaking, patient observation, a quietly unsettling possibility has emerged. The standard model of cosmology, the one built on the assumption of a perfectly constant dark energy, no longer fits the combined data quite as comfortably as it once did. A model where dark energy's strength shifts gradually over time appears to align with the evidence somewhat more naturally. The statistical case isn't yet strong enough to be called a definitive discovery. Scientists are careful, deliberately so, about that distinction. But the hint has not gone away. If anything, with each new batch of data, it has only grown a little more difficult to dismiss. What would it mean if this hint eventually solidifies into certainty? It would mean dark energy isn't the fixed, eternal property of empty space that Einstein's old cosmological constant always assumed it to be. It would mean the universe's distant future, the rip, the crunch, the freeze, isn't simply a matter of extending today's gentle, steady acceleration indefinitely into tomorrow. It would mean the story is still being written, its ending still genuinely undecided, shaped by a force that may be quietly evolving even as we try to measure it. For now, the question remains open, suspended somewhere between confirmation and uncertainty, exactly where the most interesting questions in cosmology tend to live. Astronomers continue gathering more data. DESI continues its patient nightly survey, fiber by fiber, galaxy by galaxy, adding new points to a map that already stretches across most of cosmic history. And somewhere in that growing map, hidden among 15 million points of ancient starlight, may be the first real clue to how this immense story finally ends, whether in fire, in collapse, in endless cold stillness, or in some future still waiting to reveal itself, one patient measurement at a time. Revolutions in science rarely arrive as single, dramatic announcements. More often, they begin quietly, hidden inside a number that simply refuses to behave the way everyone expected it to, appearing again and again across different teams, different methods, different years of careful observation, until ignoring it becomes harder than taking it seriously. That is roughly the shape of what has been happening with dark energy since 2024. When the DESI collaboration released its very first results, drawn from just 13 months of observation, researchers noticed something curious tucked inside the data. As they measured dark energy's influence across different chapters of cosmic history, looking billions of years into the past at different distances, the values didn't sit perfectly still. They seemed to fluctuate, ever so slightly, shifting depending on which era of the universe's history was being examined. A universe with a truly constant dark energy, the kind Einstein's old cosmological constant describes, should show the same value no matter how far back you look. Instead, the data hinted at something gently uneven, small variations that, on their own, could easily have been dismissed as statistical noise, the kind of minor wobble that often disappears once more data arrives. So scientists did what scientists do. They waited for more data, and then they looked again. By 2025, with 3 full years of observations now in hand, spanning more than 14 million galaxies and quasars, the picture hadn't grown quieter. It had grown louder. The fluctuations researchers had cautiously noted in the first year's results were not only still present in the larger dataset. They had grown more pronounced, more difficult to attribute to chance, more consistent across independent checks designed specifically to rule out hidden errors in the instruments or the analysis. At the center of this growing pattern sits that familiar parameter, W, the number physicists use to describe dark energy's equation of state, the precise relationship between its pressure and its density. For nearly 3 decades, every measurement gathered had pointed toward a value remarkably close to -1, the exact number a true, unchanging cosmological constant would require. DESI's combined analysis, drawing together its own observations with independent measurements from the cosmic microwave background, from distant supernovae, and from the subtle gravitational bending of light known as weak lensing, suggested something different. The data favored a value of W that wasn't fixed at -1 at all, and more strikingly, a value that appeared to be different in the distant past than it is today. Cosmologists describe this kind of behavior using 2 related numbers, often written as W0 and WA, one capturing dark energy strength right now, the other capturing how that strength has been changing across cosmic time. And when researchers asked which model fit the combined data more comfortably, a fixed constant, or a slowly evolving quantity, the evolving model came out ahead. This is the part of the story where it helps to slow down and sit with what that actually means, because for over 25 years, the assumption of a perfectly fixed cosmological constant had quietly become one of the bedrock pillars of modern cosmology. It sits at the heart of what scientists call the Standard Model of Cosmology, often shortened to lambda CDM, where the lambda represents exactly this unchanging dark energy, paired alongside cold dark matter to explain nearly everything astronomers observe about the large-scale universe. That model has been tested, again and again, against decades of increasingly precise data, and it has succeeded almost every single time. Few frameworks in the history of science have proven so durable. DESI's findings don't claim that lambda CDM is wrong. They suggest something gentler, but in some ways more unsettling, that one of its central, foundational assumptions, the constancy of dark energy itself, may not hold up quite as perfectly as everyone had believed. This represents the most serious challenge that assumption has faced since dark energy was first confirmed back in 1998. For more than 2 decades, no result had seriously threatened the idea of a constant, unchanging cosmological constant. This is the first one that has. What makes the finding even more intriguing is the particular direction the data seems to be pointing. The preferred values suggest that dark energy may have been somewhat stronger in the distant past than it is today, that its outward push, rather than holding perfectly steady across billions of years, may actually be gradually relaxing, growing slightly weaker as the universe continues to age. It's a subtle distinction, easy to overlook amid all the technical language, but it carries real weight. A dark energy that weakens over time behaves differently, in its long-term consequences, than one that stays constant or one that grows stronger. It nudges the universe's distant future away from some of the more extreme scenarios, like the Big Rip, and towards something gentler, though still deeply uncertain. Given how foundational the cosmological constant has been to physics for over 2 decades, it's little surprise that many cosmologists have described this development in genuinely striking terms. Some have called it one of the most exciting moments cosmology has experienced in a generation. Others have been more cautious in their language, careful to note that exciting hints have a long history of fading away once enough additional data arrives, and that real scientific caution requires waiting for that data before celebrating too loudly. But even among the most careful, measured voices in the field, there's a shared sense that something genuinely interesting is happening here, something that, if it holds up, would mark one of the most significant developments in cosmology since the discovery of cosmic acceleration itself. Part of what makes the finding so difficult to simply wave away is how consistently it appears, even when researchers deliberately try to test it from different angles. 3 independent compilations of supernova data exist, each gathered by different teams, using different telescopes, different calibration methods, different statistical approaches. Known by the names Pantheon Plus, Union 3, and the Dark Energy Survey's 5th-year sample, These three catalogs don't always agree perfectly with one another on every detail. Yet when each one was combined separately with DESI's baryon acoustic oscillation measurements, all three pointed in the same general direction, favoring an evolving dark energy over a simple constant, with the statistical confidence ranging from modestly suggestive to, in the most recent analysis, edging close to the threshold scientists generally consider strong evidence. None of the three contradicted the others. None of them made the signal disappear. And critically, the signal didn't fade as the dataset grew larger, the way many promising early hints in physics eventually do. When DESI moved from its first data release to its second, expanding from roughly 1 year of observations to 3, the evidence for evolving dark energy didn't weaken. It strengthened. Researchers ran extensive additional tests specifically designed to hunt for hidden errors, unaccounted systematic effects, subtle biases in how the data was processed, anything that might explain the pattern as an artifact rather than a real signal. None of those tests has managed to make the pattern disappear. To understand where this evidence is actually coming from, it helps to look more closely at the measurement technique sitting at the very heart of DESI's work, something called baryon acoustic oscillations, or BAO for short. The concept traces back to the universe's earliest moments, long before galaxies, long before stars, when all of existence was an unimaginably hot, dense soup of particles and light. Within that early plasma, pressure waves rippled outward from regions of slightly higher density, not unlike the way sound waves ripple outward through air, or ripples spread across the surface of a disturbed pond. These waves continued traveling outward for hundreds of thousands of years, until the universe finally cooled enough for electrons to combine with nuclei and form the first atoms. The moment that happened, the pressure driving those waves vanished, and the waves simply froze in place, leaving behind a faint, characteristic pattern, a preferred distance between regions of matter, etched permanently into the early structure of the cosmos. That frozen pattern hasn't disappeared. It has simply stretched, expanding right alongside the universe itself for over 13 billion years, leaving behind what scientists effectively treat as a cosmic ruler, a known, calculable length, baked into the universe near its very beginning, that can be measured again and again at different distances, different eras, different points in cosmic history. Just as Type Ia supernovae serve as standard candles for measuring distance, baryon acoustic oscillations serve as a kind of standard ruler, allowing astronomers to measure precisely how the universe's expansion rate has shifted, era by era, by tracking how this characteristic distance appears to change in apparent size depending on how far back in time they're looking. By measuring this same ancient ruler at many different distances, drawn from millions of galaxies and quasars spread across 11 billion years of cosmic history, DESI has been able to trace the expansion of the universe with extraordinary precision. And it's precisely this technique that has produced the unsettling tension at the center of the story. When DESI's baryon acoustic oscillation measurements are compared against predictions drawn purely from the cosmic microwave background, assuming the simplest, constant version of dark energy, the two don't align quite as comfortably as the standard model would predict. There's a mismatch, modest but persistent, sitting right at the boundary of what scientists consider mere coincidence and what they consider a genuine signal worth taking seriously. That mismatch eases, almost elegantly, the moment dark energy is allowed to evolve rather than remain fixed. Models built around a shifting dark energy, one that behaves differently at different points in cosmic history, fit the combined measurements more comfortably than models that lock dark energy into a single unchanging value. It's a small adjustment in the mathematics, but one with potentially enormous implications for how the universe's entire future might unfold. None of this has yet crossed the threshold that physicists traditionally require before declaring an outright discovery rather than a tantalizing hint. The label researchers tend to use, carefully and deliberately, is evidence, strong enough to take seriously, strong enough to reshape research priorities across the field, but not yet strong enough to retire the simpler, older model entirely. Many cosmologists, even those excited by the finding, remain cautious, noting that history offers plenty of examples where a promising anomaly, this persistent, this consistent, eventually resolved into a subtle systematic error rather than new physics. But for now, the trend keeps holding. Every additional season of data DESI gathers adds more galaxies to the map, more distance measurements to the analysis, more opportunities for this evolving signal to either fade quietly away, or solidify into something undeniable. The telescope keeps watching, night after night, on its quiet mountain in the Arizona desert, patiently adding to a picture that may, eventually, rewrite a chapter of cosmology that has stood largely unchallenged since the late 1990s. It's a strange thing to consider, drifting towards sleep beneath a sky that looks, for all the world, exactly as still and unchanging as it always has. And yet somewhere within that stillness, according to the most careful measurements ever taken, something vast may be quietly shifting, not loudly, not suddenly, but gradually, gently, the way the deepest truths about the universe so often reveal themselves. Not all at once, but one patient, careful measurement at a time. There is a particular kind of patience required in cosmology, one that separates a promising hint from an actual discovery. When a result as foundational as DESI's emerges, something that touches the very assumptions underlying the standard model of the universe, scientists don't rush toward a verdict. They turn, instead, to a slower and more deliberate process, testing the finding from every conceivable angle before allowing themselves to trust it. Part of that process involves running the numbers through extensive simulations, essentially modeling thousands of different possible versions of the universe, each built on slightly different assumptions about how dark energy behaves, and then checking which version best matches everything astronomers have actually observed. These simulations don't simulate galaxies forming or stars igniting. They simulate possibilities, mathematical universes built from different combinations of dark energy strength, its rate of change, and dozens of other cosmological parameters, compared systematically against the real data gathered from supernovae, the cosmic microwave background, and DESI's enormous map of baryon acoustic oscillations. And across an extensive range of these simulated comparisons, the same pattern that first appeared in the raw data kept reappearing. Universes where dark energy evolves over cosmic time, rather than remaining perfectly fixed, consistently produced a better statistical match to the combined observations than universes built on a strict, unchanging cosmological constant. It wasn't a single favorable result, easily explained away as a quirk of one particular analysis. It was a pattern that held up across many different statistical approaches, many different combinations of datasets, many different teams independently running their own versions of the same essential test. This consistency is part of what has led a growing number of researchers to suggest something that would have seemed almost unthinkable a few years earlier, that the standard model of cosmology, the framework that has successfully described the universe for more than 2 decades, may genuinely need to be updated. Not torn down, not discarded, but adjusted, refined, expanded to account for a dark energy that shifts gently across cosmic history rather than holding perfectly still. When researchers combine all of the major datasets together, DESI's baryon acoustic oscillation measurements, independent supernova catalogs, and the cosmic microwave background, the resulting picture continues to favor this evolving version of dark energy over the simpler, constant alternative. It's worth emphasizing just how unusual this is. Cosmology rarely sees this many independent lines of evidence point so consistently in the same direction, especially when that direction challenges something as deeply embedded as the cosmological constant. And yet, for all of that consistency, the confidence behind this finding remains, deliberately, limited. Physicists have long held themselves to an extraordinarily high bar before declaring something a genuine discovery rather than a suggestive trend, a threshold of certainty so demanding that even results this persistent haven't fully crossed it. The evidence is strong enough to take seriously, strong enough to shift research priorities across the entire field, strong enough to fill conference halls with excited discussion. But it isn't yet strong enough to rewrite the textbooks. Scientists describe results like this, sitting in that particular space between curiosity and certainty, as compelling, but not yet conclusive. Given how much rests on resolving that uncertainty, it would be unwise to rely on a single survey, however large, however careful, however many galaxies it has mapped. Real confidence in cosmology tends to come not from one extraordinary result, but from multiple, independent extraordinary results, built using different instruments, different methods, different teams, all converging on the same answer from completely different directions. Which is exactly why a second major investigation matters so deeply to this story, one that has spent decades quietly working toward this very moment, almost entirely independent of DESI itself. It's called the Dark Energy Survey, and its story stretches back further than you might expect, to a time when dark energy itself had only just been discovered. The project began taking shape in the early 2000s, not long after the original supernova surveys first revealed that the universe's expansion was accelerating. A massive international collaboration came together around a single, ambitious goal: to study this newly discovered mystery using every reliable method available, rather than relying on just one technique alone. Hundreds of scientists, eventually growing to more than 400 researchers spread across institutions on multiple continents, committed themselves to a project that would take decades to complete, long before any of them could have known exactly what it would eventually reveal. The survey's instrument of choice was a remarkable piece of engineering called the Dark Energy Camera, a 570-megapixel device built specifically for this purpose, mounted on the Victor M. Blanco 4-meter telescope, perched high in the Chilean Andes at the Cerro Tololo Inter-American Observatory. Between 2013 and 2019, Across roughly 750 nights of careful observation, this telescope patiently surveyed nearly an eighth of the entire night sky, an almost unimaginable portion of the cosmos to map in such detail. By the time the observing campaign finally wrapped, the survey had gathered information on more than 669 million galaxies, stretching across vast distances and vast stretches of cosmic time. Few surveys in the history of astronomy have reached this kind of depth and scale. What makes the Dark Energy Survey particularly distinctive isn't just its size, but its approach. From the very beginning, the project was designed around 4 entirely different methods for studying dark energy, each one approaching the same fundamental question from a completely different direction. There were the now familiar baryon acoustic oscillations, that ancient cosmic ruler frozen into the early universe. There were Type Ia supernovae, the reliable stellar explosions used as standard candles to measure vast cosmic distances. There was the study of galaxy clusters, those enormous gravitationally bound structures whose growth rate reveals how strongly dark energy has been resisting gravity's pull. And there was weak gravitational lensing, a subtler technique that traces how the combined mass of the universe gently bends and distorts the light of distant galaxies as it travels toward us, revealing the underlying distribution of both ordinary and dark matter along the way. Combining all 4 of these methods within a single survey was an extraordinarily ambitious goal, one that had been part of the project's design since its very inception, 25 years before any of it could actually be realized. For most of the survey's history, results were released incrementally, each one focusing on 1 or 2 of these techniques at a time, gradually building toward that original, more comprehensive vision. That vision finally reached completion in early 2026, when the Dark Energy Survey collaboration released its long-awaited final legacy analysis, drawing together all 6 years of observational data and, for the very first time, combining results from all 4 probes simultaneously, exactly as the original architects of the project had imagined it decades earlier. The accompanying body of research spanned 18 separate supporting papers, representing the contributions of researchers who had, in some cases, spent the greater part of their careers working toward this single, culminating release. The results that emerged were, in a very real sense, the most precise the survey had ever produced. By combining all 4 techniques together rather than relying on any single method alone, researchers achieved constraints on the universe's expansion history more than twice as tight as anything the survey had managed before. That kind of improvement matters enormously in cosmology, where even small refinements in precision can mean the difference between an intriguing hint and a confirmed certainty. Where earlier analyses had left meaningful room for different models of dark energy to remain plausible, this combined, comprehensive dataset began closing that room considerably, narrowing down which versions of the universe could still reasonably fit the evidence. And here the story takes an interesting turn, one that adds yet another layer to this already intricate puzzle. Where DESI's combined results had leaned toward an evolving dark energy, gently challenging the standard cosmological constant, the Dark Energy Survey's final analysis told a notably different story. Its results aligned most closely with the simpler, traditional model, the standard lambda CDM framework, built on a constant, unchanging dark energy, the very model that DESI's evidence had been quietly putting under pressure. It's worth sitting with that tension for a moment, rather than rushing past it. Here are two of the most ambitious, most carefully constructed cosmological surveys ever undertaken, each spanning years of painstaking observation, each analyzed by hundreds of dedicated researchers, each representing genuinely extraordinary scientific achievement, and yet, on this particular question, they currently point in subtly different directions. One leans toward a universe where dark energy quietly shifts across the eons. The other leans toward a universe where it simply doesn't. This isn't a sign that something has gone wrong with either project. It's simply where genuine scientific uncertainty currently lives, suspended between two enormous, careful bodies of evidence that haven't yet fully reconciled with one another. Researchers on both teams are continuing to dig deeper into their respective datasets, searching for subtle differences in methodology, calibration, or underlying assumptions that might help explain why two such capable surveys have arrived at slightly different conclusions. It's entirely possible that future data, combining results from DESI, the Dark Energy Survey, and other ongoing projects still gathering observations even now, will eventually resolve this tension cleanly, in one direction or the other. It's equally possible that the truth turns out to be more nuanced than either simple model currently allows, something that captures elements of both pictures at once. What remains true throughout all of this uncertainty is something quietly remarkable in itself. Two entirely independent, multi-decade scientific efforts, built using different telescopes, different techniques, different teams of researchers working largely apart from one another, have each produced cosmological measurements of staggering precision, precise enough that even subtle disagreements between them have become scientifically meaningful, worth years of careful follow-up investigation. That level of precision would have been almost unimaginable to the astronomers who first noticed those unusually dim supernovae back in the late 1990s. The discovery that started this entire chapter of cosmic history in the first place. So the question of whether dark energy is truly constant, or quietly evolving across the long arc of cosmic time, remains genuinely unresolved tonight, suspended between two of the most ambitious surveys human beings have ever conducted. More data continues arriving. More analysis continues unfolding. Somewhere in that ongoing, patient process, hidden among hundreds of millions of distant galaxies and billions of years of ancient light, the universe is likely holding the answer already, waiting, as it so often does, for science to simply catch up to what has been true all along. When researchers describe a result as more than twice as powerful as everything that came before it, it's worth pausing to appreciate what that phrase actually means. It isn't simply a modest improvement, a small refinement tucked into the margins of an already established picture. It represents a genuine leap in precision, the kind that can take a question lingering at the edges of detectability and pull it firmly into view, or alternatively, the kind that can take a promising hint and quietly dissolve it back into statistical noise. With the Dark Energy Survey's final combined analysis, achieving constraints more than twice as tight as any of its previous results, scientists finally had a tool sharp enough to ask the question that had been hanging over the field since DESI's first unsettling announcement. Is dark energy truly evolving, the way some of the evidence has suggested, or does it remain exactly as constant as the old cosmological constant always assumed? the answer that emerged wasn't a clean resolution in either direction. It was something more delicate, more genuinely uncertain, the kind of result that satisfies no one looking for a simple verdict, while quietly fascinating everyone willing to sit with nuance. When the Dark Energy Survey examined its own complete dataset, using all 4 of its probes together exactly as the project's founders had envisioned decades earlier, the results aligned most comfortably with the simpler, traditional model, the standard cosmological constant, holding steady across the history of the universe. Taken entirely on its own terms, the survey's 6 years of weak lensing measurements and galaxy clustering data didn't strongly demand anything more exotic than what physicists have assumed since the late 1990s. But cosmology rarely allows any single dataset to have the final word, and the moment researchers began combining the Dark Energy Survey's results with other major sources of evidence, the picture grew considerably more complicated. When DESI's measurements were combined with DESI's baryon acoustic oscillation data and cosmic microwave background observations, hints of evolving dark energy reappeared, though their strength shifted noticeably depending on exactly which combination of datasets was used. Pairing DESI with DESI's earlier supernova catalog, alongside cosmic microwave background measurements, produced one of the strongest signals yet recorded, edging close to a level of statistical confidence that genuinely excited the community. Yet swapping in DESI's weak lensing data instead of its supernova catalog told a noticeably quieter story, producing only a modest preference for an evolving dark energy, far short of anything resembling a confirmed discovery. This is the strange, almost paradoxical place where the science currently sits. The exact same survey, analyzed through slightly different combinations of its own internal techniques, can either gently support the idea of a changing dark energy, or comfortably accommodate the simpler, unchanging version, depending on precisely which puzzle pieces are placed alongside it. Neither model has been ruled out. Both still fit the available evidence reasonably well, which is precisely why no one in the field is yet willing to declare the question settled in either direction. What makes this particular kind of uncertainty so interesting, rather than simply frustrating, is what it reveals about where genuine scientific discovery tends to live. These aren't wild, contradictory results pointing toward completely incompatible universes. They're subtle discrepancies, small enough that they might eventually resolve into perfect agreement once even more precise data arrives, yet persistent enough that they can't simply be waved away as noise either. Slight tensions remain between different supernova catalogs, between different ways of incorporating cosmic microwave background measurements, between weak lensing results and the broader combined picture. Untangling exactly where those tensions originate, whether from subtle systematic errors still hiding somewhere in the data, or from a genuine signal that simply hasn't reached full statistical clarity yet, has become one of the most active and carefully scrutinized pursuits in modern cosmology. It's worth emphasizing what this latest, most powerful analysis has not done. It hasn't overturned the standard model of cosmology. The framework built around dark matter and a largely constant dark energy remains remarkably successful, explaining the overwhelming majority of what astronomers observe about the structure and history of the universe. What this new data has done instead is something quieter, more careful, and in its own way, more valuable. It has refined the picture, narrowing the range of models that remain plausible, sharpening exactly where the open questions still live, and revealing precisely how much more precision will be needed before this particular mystery can finally be laid to rest. Sometimes the most honest outcome science can offer isn't a dramatic new answer. It's a clearer, more carefully drawn map of exactly what remains unknown. And within that remaining uncertainty, one particular possibility has begun resurfacing in scientific conversation with renewed seriousness, a possibility many researchers had long since set aside as unlikely. The idea that the universe, rather than expanding forever into a cold and increasingly empty future, might eventually reverse course entirely and collapse. This isn't a new idea in the history of cosmology. Long before dark energy was ever discovered, the Big Crunch was one of the two primary scenarios scientists considered for how the universe might end, the other being eternal expansion. Once dark energy was confirmed in the late 1990s, and once it appeared, by every available measurement, to remain steady and unchanging, most cosmologists quietly set the collapse scenario aside. A truly constant dark energy, after all, would never weaken enough to let gravity regain the upper hand. The universe seemed destined to keep expanding, faster and faster, indefinitely. The newer evidence suggesting dark energy might be weakening over cosmic time has placed that old possibility back on the table, and some researchers have begun working through exactly what such a weakening might eventually lead to. The reasoning runs something like this. If dark energy was considerably stronger in the distant past than it is today, exactly as some of the recent combined analyses suggest, and if that weakening trend continues steadily into the future, then dark energy's outward push will keep diminishing. Meanwhile, the gravitational pull of matter, while also growing weaker as the universe expands and material spreads more thinly across an ever larger volume, may not weaken quite as quickly as dark energy itself appears to be fading. At some point, according to these calculations, the balance that currently favors dark energy could shift back the other way. Gravity could, once again, become the dominant force shaping the universe's large-scale future. Should that shift actually occur, the consequences would unfold gradually, in the patient, almost glacial timescale the universe seems to favor for nearly everything it does. The expansion that has been accelerating for billions of years would first begin to slow. Eventually, that expansion would stop altogether, reaching a kind of cosmic high-water mark before reversing entirely. From that point forward, the universe would begin contracting, with galaxies that have spent billions of years drifting apart slowly beginning to drift back together instead, retracing, in reverse, the long outward journey that began with the Big Bang itself. It's important to be clear about how speculative this particular scenario remains. Researchers exploring this possibility have been careful to note that current observations show no sign whatsoever that any such collapse has already begun. The universe, as far as every available measurement can tell, is still very much expanding, and still doing so at an accelerating pace. Even under the models that take this weakening trend most seriously, any eventual reversal lies an almost incomprehensible distance away, on the order of 20 billion years from now at the very earliest, assuming the underlying trend in the data continues to hold up under further scrutiny. There's also a deeper layer of uncertainty worth acknowledging honestly. Some of the most recent work exploring this question has gone even further, questioning not just whether dark energy is weakening, but whether the very evidence for cosmic acceleration might need to be re-examined from scratch. A handful of researchers have proposed that the supernovae used to measure cosmic expansion may not be quite as perfectly uniform as originally assumed, that subtle differences tied to the age of the stellar populations producing these explosions might be subtly distorting the brightness measurements that first revealed acceleration back in the 1990s. If that proves correct, some of these researchers argue the universe's expansion might actually be decelerating already, rather than merely approaching some far more distant future reversal. This remains a genuinely contested idea, one that most of the cosmology community continues to treat with considerable caution, since the original supernova measurements have already withstood more than 2 decades of independent scrutiny. But it illustrates just how unsettled even the most basic facts about cosmic acceleration can still become, once enough careful researchers start asking sufficiently careful questions. What ties all of these threads together? The weakening trend hinted at by DESI, the mixed signals emerging from the Dark Energy Survey, and even these more provocative re-examinations of the original supernova evidence, is a shared sense that the story of dark energy is far from finished. For more than 2 decades, the field operated under a comfortable, well-supported assumption that the universe's fate was essentially settled, drifting steadily toward an ever colder, ever emptier eternity. That comfortable certainty has given way to something more genuinely open, more authentically uncertain, in exactly the way that tends to precede some of science's most significant discoveries. Whether the universe ultimately tears itself apart in some distant big rip, drifts quietly toward an endless big freeze, or eventually reverses course entirely and collapses back into a big crunch, remains, tonight, a question without a final answer. The evidence continues accumulating, survey by survey, galaxy by galaxy, each new measurement adding another careful brushstroke to a picture still very much in progress. And somewhere within that unfinished picture, written into the light of galaxies billions of years old, the true ending of this story is most likely already determined, waiting, patiently, the way the universe always seems to wait, for science to finally catch up and read what has been there all along. If such a collapse were ever to actually unfold, the universe wouldn't simply reverse course in some sudden, dramatic instant. Before any contraction could begin, the cosmos would first need to reach the outermost edge of its expansion, a single moment representing the largest it will ever become. Picture it like the highest point of a tide, the furthest the water ever pulls from shore before gravity, patiently, begins drawing it back in. At that moment of maximum size, every galaxy would be as far from every other galaxy as it will ever get, the distances between them stretched to their absolute limit, before the long, slow process of contraction quietly begins. Whether the universe is actually approaching anything like that turning point remains, for now, entirely unknown. The honest answer is that current evidence simply isn't precise enough to say. And that uncertainty, more than anything else, is what's driving an extraordinary amount of effort across the scientific world right now, as researchers build increasingly powerful tools specifically designed to listen more closely to whatever the universe is trying to tell us. One of the more unexpected developments in this effort has come not from a telescope at all, but from advances in artificial intelligence. for decades, confirming that a particular explosion in the night sky was genuinely a Type Ia supernova, the reliable kind astronomers depend on as standard candles, required painstaking spectroscopic analysis, examining the detailed fingerprint of light from each individual event. That approach worked reasonably well when surveys were finding hundreds of these explosions. It becomes almost impossible once surveys start finding thousands, or eventually, hundreds of thousands. The Dark Energy Survey's final supernova analysis offers a glimpse of where this is heading. Drawing on more than a decade of accumulated effort, researchers there analyzed an unprecedented sample of over 1,500 supernovae, many of them classified using machine learning rather than painstaking manual spectroscopy, and from that sample, produced some of the strongest constraints on the universe's expansion ever obtained from supernova data alone. As future surveys begin discovering supernovae by the tens of thousands, this kind of AI-assisted classification won't simply be a convenience. It will become an absolute necessity, the only realistic way to sort through that much information without losing years to manual review. Alongside these AI-assisted techniques, refined supernova catalogs continue to grow more precise as well. One of the most widely used compilations, known as Pantheon Plus, brings together more than 1,500 carefully calibrated supernova measurements, painstakingly cross-checked and recalibrated to remove subtle sources of error that older catalogs hadn't fully accounted for. This catalog has already played a meaningful role in many of the combined analyses driving the recent excitement around evolving dark energy, and as it continues to be refined further, it offers researchers an increasingly reliable foundation for testing exactly how dark energy has behaved across cosmic history. Perhaps the most anticipated new tool in this entire effort is the Vera-C Rubin Observatory, an 8.4-meter telescope perched high on a mountain called Cerro Pachón in Chile, equipped with what is, quite simply, the largest digital camera ever built. After years of careful construction and testing, the observatory released its very first images to the public in June of 2025, followed by a long and careful commissioning process throughout the months that followed. By February of 2026, the observatory had begun issuing its first real-time scientific alerts, flagging supernovae, asteroids, and other changes in the night sky almost as soon as they occurred. And now, in these very early months of 2026, the observatory is beginning its main event, a 10-year survey called the Legacy Survey of Space and Time, designed to scan the entire visible southern sky every few nights, for an entire decade, creating what scientists have taken to calling the greatest cosmic movie ever made. Dark energy sits at the very heart of why this observatory exists. One of its central scientific goals involves a technique called weak gravitational lensing, sometimes described as cosmic shear, which traces how the combined gravity of matter throughout the universe subtly bends and distorts the light of distant galaxies as it travels toward us across billions of years. By mapping that distortion with extraordinary precision across enormous swaths of sky, researchers expect that within just a single year of data collection, this observatory's measurements will rival the precision DESI achieved using years of dedicated dark energy observations, offering a completely independent test of whether dark energy is truly evolving, built using an entirely different method than anything that's come before it. In a very real sense, This means the observatory is doing something close to probing the actual geometry of space-time itself. The bending of light it measures isn't simply a clever trick for studying distant galaxies. It's a direct trace of how mass curves the fabric of space, exactly as Einstein's equations describe, allowing researchers to reconstruct, with remarkable detail, how that curvature has shifted and evolved across the long history of the cosmos. Combined with its unprecedented decade-long record of nearly every visible change across the southern sky, this observatory may end up offering one of the most complete pictures of the universe's structure and evolution ever assembled. While Rubin Observatory prepares to take center stage, other instruments already in operation continue contributing meaningfully to this same broader effort. The James Webb Space Telescope, originally built primarily to study the universe's earliest galaxies and stars, has begun offering unexpected insights into dark matter as well, a mystery closely intertwined with dark energy's own story. Recent observations have revealed enormous filament-like structures threading between early galaxies, structures that may trace the underlying scaffolding of dark matter itself, the invisible framework along which ordinary matter eventually gathered to form the first galaxies. Some researchers have even proposed, based on Webb's observations, that some of the universe's very first stars may not have been ordinary fusion-powered suns at all, but extraordinary objects called dark stars, powered instead by the quiet annihilation of dark matter particles within their cores. Dark matter research has been advancing on other fronts as well, often working in close conversation with everything being learned about dark energy. Deep underground detectors, shielded from cosmic radiation by thousands of feet of rock, continue tightening the net around dark matter's possible identity, ruling out entire categories of theoretical particles with each new round of results. Other researchers have proposed entirely new indirect methods for detecting dark matter's presence, including the curious possibility that dark matter might subtly shift the color of light passing through it, leaving a faint signature that future surveys could potentially detect across enormous cosmic distances. Taken together, these efforts paint a picture of a field moving with real momentum right now. Multiple independent surveys, instruments, and analytical techniques, often developed entirely separately from one another, are converging on these same deep questions at roughly the same moment in time, each one offering a slightly different angle, a slightly different method, a slightly different way of cross-checking everything the others have found. Progress on these fronts has rarely felt this active, or this promising, in the entire history of modern cosmology. And yet, for everything actively being built and refined and launched into the sky right now, the most important lesson sitting underneath all of this work may be the simplest. The standard model of cosmology, the elegant framework built around dark matter and a steady cosmological constant, has succeeded magnificently for more than 2 decades. But success isn't the same as completeness. A growing chorus of subtle tensions, in how quickly the universe seems to be expanding today compared to predictions, in how matter appears to be clustering compared to expectations, and now, in whether dark energy itself remains perfectly fixed, has begun to suggest that this remarkably successful model may not be the final word after all. Something may still be missing from the picture, some deeper layer of physics not yet accounted for, quietly waiting at the edges of our most precise measurements. What makes this moment feel particularly significant is that some of this uncertainty wasn't entirely unexpected. Long before DESI ever released its surprising results, certain theoretical frameworks had already predicted that dark energy probably shouldn't behave like a perfectly fixed constant. Some models built around extraordinarily light hypothetical particles, sometimes called axion-like particles, suggested dark energy might naturally evolve gently over cosmic time, rather than staying frozen at one unchanging value forever. Other lines of theoretical reasoning, drawn from deeper questions in fundamental physics, have hinted at similar conclusions. In an odd way, the observational hints emerging from DESI and other surveys may simply be catching up to ideas theorists had been quietly entertaining for years, long before there was any data capable of testing them. So here, after everything, after the supernovae that first revealed acceleration nearly 30 years ago, after the patient decades spent confirming and reconfirming that strange discovery, after the staggering mismatch between quantum theory's predictions and what astronomers actually observe, after DESI's startling hint that dark energy might be weakening, after the dark energy survey's careful, nuanced, not quite conclusive results, after the quiet possibility that the universe might someday stop expanding and slowly fold back in on itself, here's where the story stands tonight. Unfinished. Genuinely unresolved. And perhaps that's exactly as it should be. Because what dark energy represents, more than any single number or equation, is a reminder of how much remains unknown about the universe we live inside of. More than 2/3 of everything that exists is built from something we still cannot fully explain, something whose true nature continues to slip just beyond our most careful measurements, even as those measurements grow more precise with every passing year. Telescopes are watching. Instruments are listening. Patient researchers, scattered across continents, are slowly assembling pieces of a puzzle whose final shape no one has seen yet. And somewhere above you tonight, in the quiet darkness between galaxies, that same invisible force is still there, doing whatever it is that it does, pushing everything gently outward, exactly as it has for billions of years already, waiting, patiently, the way mysteries this old and this vast always seem to wait, for someone, someday, to finally understand. By now, after everything that's been gathered together across this long, quiet exploration, it's worth sitting with a strange and rather humbling thought. Almost everything you've heard about dark energy tonight, its overwhelming share of the universe, its strange repulsive push, the supernovae that first revealed it, the surveys built specifically to study it, has been evidence of its effects, not its nature. Scientists can measure dark energy with extraordinary precision now. They still cannot tell you, with any real confidence, what it actually is. One of the deepest questions still sitting at the center of this mystery is whether the problem lies with dark energy itself, or with something even more fundamental, our basic understanding of space and time. For more than a century, Einstein's theory of general relativity has described gravity with remarkable success, predicting the orbits of planets, the bending of starlight, the existence of black holes, all with extraordinary accuracy. But general relativity has never been tested directly at the scale of the entire observable universe, the scale where dark energy's influence becomes overwhelming. It remains entirely possible that gravity itself behaves slightly differently at those vast distances than Einstein's equations predict, and that what we call dark energy is really just the visible symptom of a theory of space and time that needs to be gently reshaped at its largest scales. If that turns out to be true, the rewrite required wouldn't simply add a new ingredient to cosmology's recipe. It would mean reconsidering the very framework that has anchored physics for over 100 years. That's part of why the stakes attached to this question feel so unusually high. If the recent hints of evolving dark energy are eventually confirmed beyond any reasonable doubt, the implications wouldn't stay neatly contained within cosmology. They would ripple outward into nearly every corner of fundamental physics. The standard model that has guided research for more than 2 decades would need genuine revision, not a minor footnote, but a structural update to one of its central pillars. Textbooks would need rewriting. Decades of assumptions, built carefully on top of a constant cosmological constant, would need re-examining from the ground up. It's the kind of confirmation that comes along only rarely in the history of science, the kind that doesn't just add new knowledge, but reorganizes how an entire field understands its own foundations. And yet, for all the excitement surrounding these recent results, it's important to hold on to a simple, honest fact. The evidence, as compelling as it has become, is not yet definitive. Across DESI, across the Dark Energy Survey, across years of supernova catalogs and cosmic microwave background measurements, the statistical confidence behind evolving dark energy has grown steadily stronger, edging closer to the kinds of thresholds physicists usually require before declaring something truly discovered. But it hasn't crossed that final threshold completely, not yet, not with the kind of overwhelming certainty that ends debate once and for all. Which means the simpler explanation, the one Einstein himself stumbled into and later dismissed, a perfectly constant dark energy woven evenly into the fabric of empty space, cannot be ruled out either. It still fits a great deal of the available data reasonably well. It remains, by most standards, the simplest explanation still on the table, and in science, simplicity carries real weight, right up until the evidence demands something more complicated. 2 possibilities, then, both still genuinely alive. A universe where dark energy never changes, and a universe where it does. Many of the researchers working closest to this question sense that the answer may not stay hidden much longer. With Rubin Observatory now beginning its decade-long survey of the southern sky, with DESI continuing to gather still more data, with new supernova catalogs growing larger and more carefully calibrated with each passing year, the kind of precision needed to finally settle this question seems, for the first time in decades, genuinely within reach. Some scientists have described this as one of the most promising moments cosmology has experienced in a generation, a sense that something significant may be confirmed within the next handful of years, rather than remaining theoretical for decades more. Naturally, not everyone agrees on how close that resolution actually is, or even on how seriously to weigh the evidence gathered so far. Some researchers remain genuinely persuaded that dark energy is evolving, pointing to the consistency of the signal across multiple independent datasets. Others remain more cautious, noting that promising anomalies in cosmology have, more than once, eventually dissolved into subtle calibration errors once enough additional scrutiny was applied. This kind of disagreement isn't a flaw in how science works. It's closer to the opposite. Genuine debate, carried out carefully, skeptically, across years of cross-checking and reanalysis, is precisely how fragile hints either solidify into confirmed discoveries, or quietly fade away as better explanations emerge. The fact that this debate continues, actively and seriously, is itself a sign of just how significant the underlying question has become. Underneath all of this, one final possibility remains worth sitting with quietly. Dark energy itself, the very name scientists settled on more than 2 decades ago, may not even describe what it eventually turns out to be. It might be vacuum energy, an intrinsic hum built into empty space. It might be quintessence, some dynamic field shifting gently across cosmic time. It might be evidence that gravity itself behaves differently than Einstein imagined, once you zoom out far enough. Or it might be something else entirely, some possibility no one has fully imagined yet, waiting quietly at the edges of current theory for the right insight, the right measurement, the right unexpected discovery to finally bring it into view. The name dark energy may, in the end, turn out to be little more than a placeholder, a label scientists gave to a mystery before they understood what they were actually naming. It's a remarkable thing to consider, drifting toward the end of this long journey through nearly 30 years of careful, patient, often surprising science. An entire field of brilliant researchers, armed with some of the most sophisticated instruments ever built, has spent decades chasing something they still cannot fully define. And rather than that being a failure, it might be one of the most honest, most beautiful things about how science actually works. The universe doesn't reveal its deepest secrets easily, or quickly, or all at once. It reveals them slowly, reluctantly, one careful measurement at a time, to anyone patient enough to keep asking. So as this long night continues, and your thoughts drift quietly along with it, let this be the thought that lingers in that drifting place between wakefulness and sleep. After nearly 3 decades of searching, dark energy remains the greatest mystery in the universe. It shapes the fate of every galaxy, every star, and perhaps reality itself, yet we still don't know what it is.